Okay, so for this problem, we're going to be working with counting principles. So let's look at our first question. We want to figure out how many different paths lead from A to D. Well, we can look at this and can say, okay, well, there's 4 paths that take me from A to B. And I could take any of those 4. From B to C, I have 3 paths, right? I could go the upper, I could go the middle, or I could go the lower path. Right, so once I go from A to B, I now have 3 selections on going from B to C. And then if I'm going to go from C to D, right, that once I get to my node C, I have 4 different paths once again that I can travel through. So if I think about my counting principle, I've got 4 times 3 times 4 possibilities, which would be 48. So I have 48 different ways to get from this node A to this node D. Okay. If we look at this next problem, how many different triangles can be formed by connecting 3 vertices of a regular hexagon? So I can look to this and say, okay, well, if I connect these 3 vertices, right, I could think about that as triangle 1, right? And if I connect the next 3 vertices, I can think about that as triangle 2. If I connect this vertices, I can think of that as triangle 3. And I connect over here at the top, I could think about that as triangle 4. Many times, labeling our vertices can make this easier to see. So I have A, B, C, D, E, F. So really and truly, I could say I have a triangle formed by ABC. I have a triangle formed by ACD. I have a triangle formed by ADE, and I have a triangle formed by AEF. All right. So notice what really is happening. All right. I know that ABC is going to be equivalent to ACB, right? That if I go A to B to C or A to C to B, right, I'm still going to have the same triangle. It's not going to be this different triangle, which, right, of course, would be the same as if I went BCA. If I went from B, C, and A, I'm going to have the same triangle. So I can think a little bit further for this problem and say, well, wait a second, really, I've got 6 vertices. And from those 6 vertices, I need to choose 3 of them to form a triangle. But the order of selection doesn't matter, so it's going to be a combination, right? That I have 6 vertices, I need 3 of them to form a triangle, but I'm not going to care about the order of selection of those vertices. So I know that that's going to be 6 factorial divided by 3 factorial, 3 factorial. Or another way I can think about this is that I have 6 vertices I could select for my first vertex, 5 vertices I could select for my second vertex, and 4 vertices I can select for my third vertex. And then I need to divide out by the ways that I could select those vertices. So in other words, what I have is 6 times 5 times 4 divided by 3 factorial. And that's just going to leave me with 20. 5 times 4, because 6 and 3 factorial are equal. And I'm going to have 20 different ways that I could form the triangle. So I could list them all out, but really that's more than necessary. And for our purposes, right, doing things by exhaustion or doing things by guess and check isn't going to be how we want to do them. We want to see what the pattern is and then work within our pattern. Okay. If I look to my next question, how many permutations on these symbols if they're taken 2 at a time? So I have a permutation, so the order matters, right? So for C, I've got 4 factorial divided by 2 factorial, which really is, I have 4 symbols, so I've got 4 choices for the first symbol and 3 choices for the second symbol, so there are 12 permutations. Now, what are those 12 permutations? Well, I could have P and then Q, I could have P and then R. I could have P and then S. Right, because it does ask me to list them. Then I could have Q as my first letter, all right, and then Q could be then with P, Q could be then with R, Q could be then with S. Of course, it could be R as my first letter, R with P, R with Q, R with S. And then finally, I could have S as my first letter, S with P, S with Q, and S with R, which gives me my 12 permutations. Now, what if the order of selection didn't matter? What if the order of selection didn't matter? Then I would say, hey, 4 times 3, but then the ways I could organize that, which is divided by 2 factorial, which is the same thing as 4 choose 2. Well, this one up here would be 4 permutation 2. Right? Now, my 4 choose 2, if I'm working with this environment, I can say, well, P and Q, Q and P, those represent the same things. Right? That P and R and P, right? Those represent the same. And I could go through and pair up in the different ways that I have these items, right? That P and S could be paired with S and P. These two, right, are essentially the same. These two are essentially the same. And then last but not least, I have that Q and S goes with S and Q. So I have 1, 2, 3, 4, 5, 6, which is what I'm expecting, right? That I have 6 combinations while I have 12 permutations. Okay. Then for E, if I consider E, I have this expression with factorials. So I'm going to rewrite that expression as n minus 1 factorial plus n plus 1 times n minus 1 factorial all over n minus 1 factorial. So notice now that I have an n minus 1 factorial in each of my terms. So for the numerator, if I factored out, I would have n minus 1 factorial multiplied by 1 plus n plus 1 times n, all right, all over n minus 1 factorial. Those n minus 1 factorials, because they're common factors, will cancel. And the result that I would have is that I would have n squared plus n plus 1. So if I had this set up as an equation, right, if I had this set up as an equation, let's say I said, you know, not to simplify the expression, but instead I said solve, and I said, I want this to equal, let's see here, let's say we wanted it to equal, let's say we wanted it to equal 3. All right, so what values of n will have me equal 3? Well, I'll be able to say, okay, well, that simplifies to be n squared plus n plus 1 being equal to 3, which will mean that n squared plus n minus 2 needs to equal 0. And I would be able to see that I have n, what would this be, plus 2 times n minus 1 being equal to 0, which would mean that n either equals negative 2 or n equals positive 1. But here's where we're going to have to be careful, right? If n is equal to negative 2, I'm going to have to determine, is it okay to have a negative factorial? And that's something that we'll discuss at a later time. If n equals 1, well, I have 0 factorial. Well, 0 factorial is fine because 0 factorial is defined to be 1. And how many ways can I organize 0 objects? Well, there's only one way. There's no organization for it. Right? So if I had this set up, I'd be able to say, okay, well, yes, for sure. 0 factorial plus 2 factorial divided by 0 factorial is, in fact, 3. But want to be careful about working with the negative and saying what is going to be that negative factorial. If you want, feel free to look at what happens with negative factorials. And lastly, rewrite our binomial coefficient. So with f, with our binomial coefficient, right, that 9 choose 2 is equivalent to saying 9 choose 2. Right, different ways that we could write this, which is going to be 9 factorial divided by 7 factorial 2 factorial. Or visually, I have 9 items. I need to select 2 of them, so that's 9 times 8. But then I need to divide out by the ways I could organize those 2 items, in this case 2 factorial. So 9 factorial divided by 7 factorial 2 factorial is 9 times 8 divided by 2 times 1, which then is going to be 9 times 4, which would be 36. Okay. So a variety of ways that we can work with our counting principles, and we understand how these can be related to, in particular with our binomial coefficient, related to that binomial theorem. Okay. Thank you very much for your time.